this second chapter of trigonometry, we were going to be extending our knowledge of the trig functions. In this lesson, we will be looking at sum and difference identities.
So when we talk about sum and difference identities, what we're looking at here are the identities that you see right here in this box. And these will all be provided for you. You don't need to memorize them. They will be given to you on your formula sheet here. They are, however, a way of thinking about trigonometric functions that is, for some of you, can take a little bit of getting used to. Now, what we're going to do here is we're not going to go through the process of proving these to you like we did with some of the previous identities here. You're just going to have to kind of accept that these are true here. Let me just illustrate at least one idea though. Let's take a quick look at this first one here. I'll zoom in on this. Look at this first one. Sine of alpha plus beta should be written as the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Now I'm going to illustrate a common misunderstanding here. Often you'll see people that'll do this. They'll see the sine of 30 degrees plus 60 degrees. And they'll say, oh my gosh, it's sine. You just distribute across sine of 30 degrees plus the sine of 60 degrees. It has to be that. Of course it does. Because the sine of 30 is 1/2 and the sine of 60 is root 3 over 2. We know those from special triangles or from the unit circle. And so we would write this as 1 plus the square root of 3 over 2. And yet over here someone might say, hey, well wait a second, sine 30 plus 60, that's 90. So this is just the sine of 90 and we know that that's equal to 1. Because it's so obvious that 1 is equal to 1 plus root 3 over 2, right? Right? Yeah, wrong. No, that doesn't work at all. That's not at all the way that works. Sine isn't something that can be distributed across the terms when there are multiple terms that show up in its argument. That's true for cosine, secant, cosecant, tangent, cotangent, all of them. None of the trig functions distribute across terms in their argument. Okay, they're an operator, they're a function that operates on those values a little differently than that. Okay, this is not, the mistake that gets made here is sometimes people treat this as like it's a multiplication. This is sine times 30 plus 60. That's not true. It's the sine of 30 plus 60, which is a different operation here. And that's why all of these exist here. Now, specifically between, sine and cosine, I'll just show you a little pattern here. For sine, notice that it's always sine cos, and then we just change the angle here. And if it's an addition sign here, it's addition here. If it's subtraction, there's subtraction here. Now, you can't just do the sine cos willy-nilly though. Whatever comes first, whatever angle comes first, you have to take the sine of it first. So it has to be sine cos, and then here minus cos sine. For cosine, notice it's going to be cos, sine, sine. Okay, and it's always like that. And if it's addition in between here, it becomes subtraction. If it's subtraction here, it becomes addition. Changes signs here. And then inside here for tangent, you've got a kind of a pattern here. If you see addition here, it's addition. Subtraction becomes subtraction. But then what happens is down in the denominator, it switches signs right there. But again, you don't really have to memorize it. Really what you need to do is you need to be aware that there is a rule here so that you don't just inadvertently start distributing that through. Okay, be aware that there's a rule and you should probably go look it up on your formula sheet before you apply it.
Write each expression as a single trigonometric function. Sine of 48 degrees multiplied by the cosine of 17 degrees minus the cosine of 48 degrees times the sine of 17 degrees.
Okay, so in this case right here, the trick to writing this as a single trigonometric function is just recognizing the pattern. So I've got sine cos minus cos sine. Now, sine cos, cosine, I'm changing the operations. I've got two different operations. This is definitely a sine here. And remember that sine copies the operation that you're seeing in between here. So this is going to be 48 degrees, the first angle, minus the second angle. And so this will become the sine of, what is that, 31 degrees. That's the expression that we're looking for here.
The cosine of 7 pi over 12 times the cosine of pi over 3 plus the sine of 7 pi over 12 multiplied by the sine of pi over 3.
All right, once again, it's a matter of just recognizing the pattern and putting these together. And notice in this case, I've got cos, sine. So that reminds me of the the cosine here, and we can look up here and see it, cos, cosine, sine, cos, cosine, sine. And notice, again, if it's addition here, then I know that within this, this expression here, this argument, it's going to be subtraction. And so we take the first angle that we see, and we're going to subtract the second angle. Now, that just requires common denominators, so I get 7 pi over 12 minus, and then pi over 3 will become 4 pi over 12. Okay, because I multiply numerator and denominator by 4. Now, 7 pi over 12 minus 4 pi over 12 is going to be the cosine of 3 pi over 12. But please don't leave it like that. Please, I beg you, don't leave it like that. 3 over 12 is a quarter, so this is going to be the cosine of pi over 4. That's actually what this one reduces down to. In fact, we could even evaluate that right now and get an exact form, but that's not what it's asking for.
Simplify and evaluate. The cosine of 75 degrees multiplied by the cosine of 15 degrees minus the sine of 75 degrees multiplied by the sine of 15 degrees.
So this question asks us to go just one step beyond what we did in the previous question, so we're going to simplify and then evaluate. Now, again, notice the pattern. I've got a cos, cos minus sine, sine. So that is a cosine expression. There's subtraction in between, so it's going to be addition in between. So this is going to end up being the first angle plus the second angle. Okay, well, 75 plus 15, that is conveniently 90 degrees. Okay, and think about it a little bit. What is the cosine of 90 degrees? 0. Because remember, along the unit circle, cosine gets associated with the x-coordinate, and when you're at 90 degrees, or you're at basically the top of the unit circle, the x-coordinate there is 0.
The tangent of 15 pi over 8 minus the tangent of 3 pi over 8, all divided by 1 plus the tangent of 15 pi over 8 multiplied by the tangent of 3 pi over 8.
All right, well, I think in this case here, it's pretty obvious that this has got to be a tangent, okay, a sum or difference of the tangent ratios here. Now, notice the pattern, though. I've got a subtraction up here, an addition up here, and that corresponds to this guy right here, subtraction and addition, and we know that that means that there's got to be a subtraction within the argument here. So we take the first angle, the 15 pi over 8, and we will subtract the second angle, 3 pi over 8. Now, it's convenient that they gave it to us already in common denominators here. So this is going to become 12 pi over 8. And that reduces down to just 3 pi over 2. Okay, now that's convenient because 3 pi over 2 is at the bottom of the unit circle. Just think about that. It's essentially 270 degrees. 3 pi over 2, it's the bottom of the unit circle. Tangent is the y-coordinate over the x-coordinate. So in this case, that's going to be, if you will, negative 1 over 0. Which is really undefined. Okay, so the value that we're looking for here is actually, we want this thing to become undefined at the end.
Simplify each expression using a sum identity. The sine of 90 degrees plus theta.
All right, in this case here, we want to simplify this expression, and we're going to use a sum identity here. Now, I like questions like this. I really do. I think they're an interesting question. They do show up later on. Okay, when you take calculus, you're going to see stuff like this happen fairly frequently. What makes this interesting here is the 90 degrees. Okay, because we know the value of sine at 90 degrees, and it's a nice one. Okay, it's just the number 1 here. But when we expand this, we are going to get the sine of 90 degrees, the cosine of theta, and then plus, because sine maintains that operation, the cosine of 90 degrees, and then the sine of theta. Now, the sine of 90 is 1, so this becomes 1 times the cosine of theta. But the cosine of theta is 0 times the sine of theta. And so that makes this second term actually disappear. And so this is just equal to the cosine of theta. You could almost think of that as an identity. This is the cosine of theta. I like that. It's good.
The cosine of 3 pi over 2 minus a.
All right, really similar sort of question to the one that we just did, except this one's in radians, and we're looking at cosine. Remember how cosine works. This is going to be the cos of the first angle times the cos of the second angle, and then cosine does not maintain that operation, so this is going to become addition. So plus the sine of 3 pi over 2 times the sine of a. Now, the cosine of 3 pi over 2. 3 pi over 2 is on the y-axis in the negative direction. And the value of x at that point is going to be 0. So the cosine will be 0. This is going to be 0 times the cosine of a. The sine, when you're down there, is -1. So this is, sorry, the y-coordinate is -1, which means the sine will be -1. So this becomes -1 times the sine of a. And so 0 times the cosine of a, that term disappears. And so this is just the negative sine of a. And again, it's kind of like an identity here. I know that something like this would be equal to the negative sine of a. It doesn't matter what the value of a is, that's true.
Determine the exact value of each of the following. The cosine of 15 degrees.
All right, here's a really common style of question. This is the kind of question you really should expect to be on the exam. Heck, you could even expect it to be on the diploma exam. It's just that common here. Cosine of 15 degrees. Okay, now I don't have that off of the unit circle, but I do have angles that I can combine to get 15 degrees. For example, I could make this, let's say 45 degrees minus 30 degrees. Now I do know the cosine and sine of 45 and 30 because those are unit circle angles here. And I can use this expression right here and expand on it using one of the identities. This is going to become the cosine of 45 degrees times the cosine of 30 degrees. Now because it's subtraction in between, cosine makes it positive. Sine of 45 degrees, sine of 30 degrees. And now I can plug those values in. This becomes the square root of 2 over 2. That's the cosine of 45. The cosine of 30 is root 3 over 2 plus... Okay, the sine of 45 is just like cosine, that is root 2 over 2. That's the one spot where they overlap. And the sine of 30 is 1/2. All right, now, notice the denominator here is going to end up being 4, so will the denominator here. So this is all out of 4. In this first term, when I multiply those two together, I'm going to get root 6. Root 2 times root 3 is root 6. You just multiply the radicands together. Plus, root 2 times 1 is just root 2. And so that's the exact form of that. You really can't do much more with it other than just to write it like that. I can't cancel 2's out here because remember, although there's a factor of 2 here, there isn't a factor of 2 here. This isn't 6. This is root 6. Root 6 is kind of a crazy decimal. It's not an even number. Okay, just like root 2. This is not 2. This is root 2. And so I can't cancel out values here. That's about as good as that's going to get.
The tangent of 195 degrees.
Okay, now this question here tends to be a little bit involved. Okay, I'll throw that out there right now. This one here is going to be kind of a big one, but I'm going to give you a little bit of advice with this one as we go through it, and hopefully I'll help you avoid a bit of a pitfall here. First thing that I want to do here is I want to, because I'm really lazy here, I'm going to reduce this down to a trig expression in terms of a reference angle. So first of all, I know that 195 is in quadrant 3, and thankfully tangent is positive in quadrant 3, so that's good. The reference angle here is 15 degrees. Now, I'm going to keep going horizontally here because I have a feeling I'm going to have to wrap around and keep going here. Now, 15 degrees could be broken up. I could make this 60 degrees minus, I could make it 60 degrees minus 45 or 45 minus 30. My advice to you is to make this 60 degrees minus 45 degrees. And I'll explain my reasoning in just a moment when we start to fill in some of the values here. Now, this becomes, okay, tangent of 60 degrees plus the tangent, oh, sorry, I bet you I got that backwards, yep. I'm so aware of the sign having to change at one point that I forgot. It stays the same here. Where it changes is down here. So this becomes 1 plus the tangent of 60 degrees, tangent of 45 degrees. Now here's where the real issue kicks in. The tangent of 60 degrees is just root 3. And the tangent of 45 degrees is 1. And so this becomes 1 plus root 3 times 1. It's just 1 plus root 3. Now, the reason why 60 degrees is better is because if you used 30 degrees, you're going to run into the issue here where the tangent of 30 degrees is 1 over root 3, okay, or if you will, root 3 over 3. So you're going to introduce this fraction inside this fraction. And then you're going to have to do a fair bit more work here. This is just kind of the lazy way out of that problem here. I don't need to worry about that. Now, however, this may not be an acceptable answer. It may be required of me to rationalize the denominator, which means I'm going to have to multiply numerator and denominator here by 1 minus root 3. Okay? So now, bear this in mind. I'm going to come over here and I'm going to write that out. So in the denominator, I've got 1 plus root 3 times 1 minus root 3. That's going to end up being, that's the difference of squares, right? When I multiply that out, so it's going to be 1 minus 3. Okay, so over here, put this down. This is going to be in the denominator, 1 minus 3. Oh, yeah, I got that. Up here, this is going to be root 3 minus 3. Okay, when I distribute that out, so root 3 minus 3. And then when I distribute the negative 1 plus root 3. So negative 1 plus root 3. Okay, well, the denominator simplifies down nicely to negative 2. That's fine. I'm going to have a negative 3 and a negative 1, so that's negative 4 plus 2 root 3. Now, not quite done yet, though. Because I'm dividing by a monomial, I can actually distribute that monomial to both of those terms. So negative 4 divided by negative 2 is positive 2. Negative 2 divided by negative 2 is going to be negative 1. And so this whole answer reduces down quite nicely to 2 minus root 3, but it took a while to get there. Now, if we'd used 30 degrees, it would have taken us a little bit longer to get there. So 60 degrees is just kind of a nice little alternate way of getting around that problem. Still gets us there, but just a little bit quicker.
The sine of 17 pi over 12.
All right. Now, this one here is in radians. Now, to let you know right now, it doesn't, because we're looking for the ratio, the exact value of the ratio, it doesn't matter whether you're in radians or degrees. Okay, it makes absolutely no difference. So my advice to you is, let's do this in degrees. It's a little bit easier to see the relationships here if you're in degrees. So we can convert, because we've looked at this before, we can convert 17 pi over 12 into degrees, and then that becomes the sine of, what is this, 255 degrees. Okay, that's a good start. That's a good start. Now what I'm going to do here is I want to reduce this one to a reference angle, because it's easier for me to reduce this one than it is to reduce this one in a way that really makes sense to me. Okay, now 255 is in quadrant 3, so I know sine is negative in quadrant 3. And then 255 minus 180 is going to end up giving me 75 degrees. Okay, there we go. So now I know that this is going to equal the negative sine of, and then the way I get 75 here would be to take 30 degrees and add 45 to it. Okay, remember I'm trying to grab my unit circle angles here as often as I can, because those are the ones I know all the trig ratios for. So now, remember, the sine does not distribute through. I gotta go to my sum and difference identities. Now, the identity happens here. The sine of 30 plus 45 happens before the negative gets multiplied through. So when I do the identity here, I'm going to put brackets around the expansion. So this will be the sine of 30 cosine of 45 plus the sine of 45 cosine of 30. And again in brackets there. Because I want that negative to be applied to the whole thing. Okay, just like it is in the previous step here. Okay, now I'm just going to apply the values I know. I know the sine of 30 is a half. I know that cosine of 45 is root 2 over 2. I know that the sine of 45 is root 2 over 2. And I know that the cosine of 30 is root 3 over 2. Now, I recognize that. I had a very, very similar ratio pop out just a little while ago here. Okay, leave that negative up front here. I know that the denominators are going to be 4. And this first term is going to be root 2, and this second term will end up being root 6. It's the exact same numbers I saw before, but this time with a negative in front. Now, I could probably leave it like that. That's fine. Or if you want, you could distribute the negative through, make that negative root 2 minus root 6 over 4. They're both fine. They're both equally correct. It's up to you.
If angle A and angle B are both in quadrant 1, and the sine of A is 3/5 and the cosine of B is 5/13, evaluate the cosine of A minus B.
Okay, I like this question. I really do. If I was going to come up with a diploma question and I had to be from identities here, I like this question because it hits a couple of outcomes simultaneously. It's wonderful. Okay, so A and B are both in quadrant 1. Okay, that's great. Then you were told what sine of A is, what cosine of B is, and then you're asked to evaluate the cosine of AB. Now, this is where I kind of want to start with this. This is my goal. Let's go and talk about that. So the cosine of A minus B is going to equal, okay, based on the identities that I've been given, cosine of A, cosine of B, plus the sine of A, sine of B. Oops, sorry, that's not a B. I was going to write an A again. Sine of B here. Now, I know the sine of A is 3/5, and I know the cosine of B is 5/13. Wonderful. What I don't know is the cosine of A. I don't know the sine of B. So this is where I come over here, and I'm going to draw these things out. Okay, so I know that A is in the first quadrant, and I know, okay, that the sine of A is 3/5. Now think about sine of A. I know that that is equal to the opposite side, or the y-coordinate, over the hypotenuse. Now, I would hope that you'd have something like this memorized here, that you would recognize this triangle here. If you don't, you can just use the Pythagorean theorem to get this. But I would hope that it would be pretty clear to you pretty quickly that this has got to be 4. Okay, so angle A is part of the 3, 4, 5 Pythagorean triplet. Now over here with the cosine, we're told that B is in the first quadrant again. So here's B. But this time we're told that the cosine is 5/13. And remember, cosine is the x value over the hypotenuse, or the r value there. And again, this is another Pythagorean triplet. If you don't know what the answer is, if you don't know what the y-coordinate is, that's fine. Just use the Pythagorean theorem. Okay? It'll work just great here. However, I would hope that you would recognize that triangle as the 5, 12, 13 Pythagorean triplet. They use these ones a lot, is all I'm trying to say here, is that these numbers work out beautifully. The triangles are fairly small, so they're that kind of a go-to triangle for math teachers here. So now I needed the cosine of A. Okay, well, here's A. Cosine is going to be the x-coordinate over the r here, so 4/5. I need the sine of B. That's going to be the y-coordinate over the r value here, or the y over the hypotenuse, so that's going to be 12/13. Okay, now let's put this together. Now notice that the denominators are going to be the same in both cases, and that's wonderful. That's going to be, what is it, 65? And then 4 times 5 is 20. 3 times 12 is 36. And there we go. 20 plus 36 is going to be 56/65. So that's the exact value of the cosine of A minus B.
If the sine of A plus B is 0.766 and the sine of A minus B is 0.342, find the value of 2 sine A cos B to the nearest thousandth.
All right, this is kind of a cute, well, cute I guess is a relative term, but it's kind of an interesting little question here. One way of looking at these identities, it's maybe a little different than we would normally do, and kind of a throwback to Math 10 actually. Okay, so we're told that the sine of A plus B, and I'm going to write it like this, the sine of A plus B is 0.766. Now, what that means to me, okay, is that 0.766 is going to be the sine of A cosine of B, okay, plus the sine of B cosine of A. Then we're told that 0.342 is going to be the sine of A minus B, and that is going to be the sine of A cosine of B. Oh, look at that. Those are identical. I wonder if that's going to play a factor here. Minus the sine of B, sorry, yeah, no, that's right, cosine of A. That's exactly what I meant to say here. Now, so look at what I've got here. Look at those two. Those two are identical. Now, what I'm being asked to find is what 2 times the sine of A cosine of B is. Sine of A cosine of B. You know what? If I just add those two equations together, okay, I will get 2 sine A cosine of B. And notice that what happens to these terms, they're the exact same but opposite signs, so they will cancel. Now all I got to do is add what they're equal to. If I'm adding the two equations together on the right-hand side, I'm going to add what's on the left-hand side as well. So what are we going to get? We're going to get 8, what is 1 point, is that 1.108? 8, 10, yep, 1.108. And there the answer is to the nearest thousandth. I like that. Kind of a nice little reference back to solving systems of equations in Math 10.